Hello everybody. I want to give you guys just a little overview of this week's lab because we're doing things a little bit differently this week due to the fact that this is a little bit difficult for me to translate over to a virtual platform. It's a very visual sort of lab, so I just wanted to make it clear to everybody how we're going to handle this student data this week. First, for part A, we have our different white light sources here. And in lieu of being able to actually see these in person, what I have here are some pictures that I included at the end of the PDF. So if we go all the way down, we can see the blacklight CFL, and we get an image of that. Our warm white light CFL, where's that? Right here. And then the bright white CFL or LED right here. So you guys can use these pictures to recreate an image up here for this section. And then for the second part, for part B, we have lithium chloride, magnesium sulfate, and strontium chloride. It's going to be the metals of these compounds that are going to give us our emission spectrum. And we can come down here. And for instance, lithium chloride, we can come down here and we can take a look at the lithium one. And then we can recreate that up here in our data sheet. And draw out our lines on there. For the next part, we have our unknown lamp. And you're going to be able to match that with the one of these guys down here and tell me what that lamp was. And then we have our data for the hydrogen lamp, which I'm going to show you a clever way to do this a little bit better so that we can get good values for each one of these lines when we're making our plot here. In this video, I want to show you guys a technique for being a little bit more quantitative with our results in this week's experiment. And I think the best way to think about this is to start off by thinking about a map. So in this map, I have down here what they call a map scale. And this is a distance that corresponds in this case to 1,000 feet. And what the map scale allows me to do is, regardless of how large or small I print off the map, I can come down here with my ruler and I can measure this distance. Okay, so that's going to be 10, 20, not quite 25. I'll say that that's going to be 24 millimeters right there. Now, if I want to know the distance between the University of Michigan and Mott Community College, I can measure that distance as well. So I'll put this roughly at the center there, roughly at the center there. I'll draw a line. And I'm going to call that, we'll do 105 millimeters. Now, since I know that 24 millimeters is going to correspond to 1,000 feet, I can use this as a conversion factor. And if I multiply that by 105 millimeters, I can calculate the number of feet between these two and roughly guess that out. as 4,375 feet. Let's see how we can apply what we saw with the map to our data this week. So here, our scale is going to be pretty much any distance along this scale right here. For instance, we know that the distance between here and here, 400 and 450 nanometers, is going to be 50 nanometers. We can put our ruler down on there, and we'll see that this distance is pretty much perfectly 25 millimeters. Our conversion factor, therefore, is going to be the 50 nanometers, that's the difference between those 2 points, divided by 25 millimeters, or 2 nanometers per millimeter. And we have a very convenient conversion factor that we can use here. If we want to know the wavelength of this middle blue line right here, we can figure out what that distance is by putting our ruler down here. And I'm going to say that that is right about 43 millimeters. Now we do have one thing that's going to be a little different than our map example here, and that is that we started off at 400 nanometers. So we need to add this in. So we're going to start off with 400 nanometers, and we're going to add to that our 43 millimeters. But we need this to have the same units as this to add them together. So we use our conversion factor of 2 nanometers per millimeter. We can see then that the millimeters are going to cancel. And we get 400 nanometers plus 86 nanometers. This is going to be 86 nanometers. We add those together, and we can see that this blue line is roughly at 486 nanometers, which makes sense. If this is 450, halfway point here would be 475. It's a little higher than that. So 486 nanometers passes our sanity check, and we have a pretty good guesstimate for where this line is now. If we wanted to do this far red line, we can put our ruler down on it. And I'm going to say that that's just about 129 millimeters. And I can do the exact same thing here. I can do 400 nanometers plus that 129 millimeters. 2 nanometers for every millimeter. That comes out to 400 nanometers plus 258 nanometers. Again, we know that our millimeters are going to cancel here. And I get 658 nanometers, a little past 650. So again, that checks out and passes our sanity check. Now this is going to work regardless of what your actual sheet looks like. However you print this off with your scaling, your printer and stuff. Even if you had like a tablet or something like that, you could put the ruler up to that. So you may not get a conversion factor that's quite as nice as mine of 2 nanometers per millimeter, but you're going to be able to reproduce this for yourself. And that's kind of the beauty of this technique, is it doesn't really matter what this looks like, just so long as this scale is here for us to work with. And we get pretty good values, not quite as nice as we could with some more sophisticated techniques, but given the equipment that we have in this lab and the data that we're given, these are going to be pretty good values for you guys to use to make up your graphs later.